Hello everyone, I'm Yuze Wang from Beihang University. It's my pleasure to present our work, taking language-embedded 3D Gaussian splatting into the wild. Over the past few decades, researchers have leveraged internet photos to reconstruct historic landmarks in 3D by using the unconstrained photo collections, which usually contain the transient occluders and appearance variants. These approaches allow people to explore and navigate historic sites in an immersive way. However, for learning about the architectural styles and structural knowledge, people still primarily rely on the text-image pairs, lacking the immersive direct visual experience. This prompts a compelling question. Can we take inspiration from the successful 3D in the wild reconstruction methods to achieve the low-cost, fine-grained 3D understanding of architectural components from the internet-sourced unconstrained photo collections? So recently, some methods, such as the LE Gaussians, to utilize the well-captured photos collection to extracting the language features using clip to reconstruct the language-embedded 3D Gaussian. This enables open vocabulary queries and segmentation for any object in the scene. However, these methods struggle to adapt the unconstrained photo collection with appearance variance due to the lighting changes and the transient occluders, such as the tourist photos of the Trevi Ocean collected from the internet. In this work, we take language-embedded 3D Gaussian splatting into the wild. Given an unconstrained photo collections as input, our method enabled the high-quality open vocabulary segmentation, and we demonstrate a very applications. Our key contributions are summarized as follows: a framework for 3D language field reconstruction from the unconstrained photo collections, a benchmark for evaluating the open vocabulary segmentation of the building components, state-of-the-art segmentation results with diverse applications. Now, let's dive into the proposed pipeline. We start with the multi-appearance pixel-level language feature extraction. Given an unconstrained photo collection, our first step is to reconstruct a 3D Gaussian radiance field using the existing in the wild methods. Next, from the extract same viewpoints as the original photos, we render multiple novel appearances with varying appearances. For instance, the same scene at the night or the day, the raining or the sunny, but they are all without the transient occluders. Both the original images and the appearance renderings are then fed into a pixel-level clip encoder. Use the clip features, we compute two types of uncertainty maps: an appearance uncertainty maps, which qualifies how much the features vary across the different lightings or weather conditions, and a transient uncertainty map, designing to measure the likelihood of the transient occluders at right at the language feature level. Moving on the transient uncertainty await autoencoder, storing the high-dimension language features for every 3D Gaussian requires massive memory. So we found that to training this autoencoder on all features across all appearance is too slow, and simply averaging them beforehand actually caused a notable performance drop because it blurs the scene-specific feature space. So we identify a simple yet high efficient solution. We train the autoencoder using only the clip features from the original images, but we weight the loss using our transient uncertainty map. Simply put, the regions with high uncertainty, like the moving pedestrians, they receive the smaller gradients to minimize their impact, while the static, clean regions, we greatly propagate more gradients. Finally, we build our multi-appearance long-range embedded 3D Gaussian. Each Gaussian is assigned n additional long-range features to learn one original appearance and n-1 normal appearances. In our experiments, we set the n equals 4. We also utilize a tile-based renderation to ensure the rendering remains highly efficient. Once trained, we perform open vocabulary queries. Given a text query and a specific camera viewport, we first render the feature maps across the multiple appearances. We then compute the score maps by combining this with the text query's clip features. Lastly, we apply a novel background filter to suppress the irrelevant outdoor backgrounds, and then we ensemble these score maps to get our final, clean, open vocabulary segmentation results. So since no benchmark provides unconstrained photo collection with ground truth open vocabulary segmentation, we introduced the PTOVS building on the phototourism. It includes 7 landmark scenes with 10 to 12 annotated segmentation maps per scene, covering the landmark-specific open vocabulary concepts. We compare our approach to existing baselines, adapt for the in-the-wild scene 3D Gaussian-based open vocabulary scene understanding method, including the long splat, feature 3D Gaussian, Gaussian group, and LE Gaussians. So, as shown in the figure and table, the proposed method achieved the SOTA results. So this is the video results of the Travis function. We showcase the original renderings, learning language field, and the open vocabulary queries such as relief and oceanness. And this is the video results of the Brandenburg gate. We show the query results of the iron cross and the column. We demonstrate that our method can seamlessly integrate with the in-the-wild reconstruction approaches, enabling the interactive roaming and the open vocabulary queries, which provides user with a more immersive experience. Now we show the application of the architectural style pattern recognition. Our method accurately identifies the architectural styles with the multi-wheel voting strategy. Interestingly, it is able to visualize in the heat map what makes the Travis function a bakery building. And we demonstrate the application for 3D scene editing. Given an original reconstruct 3D scenes like Travis function. With our method, 3D content can be efficiently extracted with the text queries, such as querying the oceanness and the wind horse. Our method can then seamlessly integrate with the downstream 3D Gaussian editing tools, enabling actions such as the scaling up the oceanness, duplicate the wind house. Thank you everyone, that's all for my presentation. Thank you for listening.